lesson, you are going to learn what is reversible reaction, dynamic equilibrium, and the law of mass action. And later you will see the characteristics of a system in equilibrium or dynamic equilibrium, and then we will see on how to interpret the curve of concentration, reactant, and product against time for a reversible reaction. Before we start with the different types of chemical reaction in chemistry, let's watch a video on reversible reaction. So please scan this QR code to watch the video. The fundamentals of chemical reaction in chemistry is when a reactant will be consumed in order to form the product. So the chemical reactions in chemistry can occur or can happen in two types of direction. Okay, the first one we call it as irreversible reaction. Okay, tidak balas yang tidak berbalik, ataupun it is a one direction reaction. And the other one is reversible reaction, iaitu tindak balas berbalik. Irreversible reaction or tindak balas tidak berbalik ataupun one direction reaction is a chemical reaction that will go towards completion. So in irreversible reaction, all reactants will be consumed in order to form the product. This reaction we proceed in one direction, iaitu in forward reaction sahaja. Kenapa forward? Kerana daripada reaktan akan terus diguna pakai untuk menghasilkan produk. And reaction will stop when reactant is completely converted to the products. And the arrow of reaction will pointing from left to right, okay, menunjukkan daripada reaktan menghasilkan produk. And this reaction will proceed towards completion of the reaction, di mana kesemua reactants akan diguna pakai untuk menghasilkan produk. So the example of irreversible reaction adalah growth of plants, formation of bread using milk, cooking egg, rusting of iron, dan juga combustion. Okay, so all this example menunjukkan bahawa once product has been formed, there's no way for the product boleh berpatah balik semula untuk membentuk reactants. So basically, ini adalah irreversible reaction. And please remember, in irreversible reaction, kita akan gunakan anak panah one-way direction. Menunjukkan bahawa kesemua reactants will be consumed in order to form these products. Dan setelah produk ini terbentuk, there's no way untuk kita patah balik untuk membentuk the reactant. So this is the criteria of the irreversible reaction. The other type of chemical reaction is reversible reaction ataupun tindak balas berbalik. In reversible reaction, chemical reactions does not go to completion. Maksudnya di sini adalah dalam tindak balas reversible ini, reactants tidak akan digunakan sehingga habis untuk menghasilkan this product. Reaction will proceed in both forward and reverse direction. And arrow of reaction to be used in this chemical equation adalah double-headed arrow like this. Okay, so this double-headed arrow menunjukkan bahawa from this 2 kepada this HI, ini adalah merujuk kepada forward reaction, dan apabila HI berpatah balik membentuk this 2, this is so-called reverse reaction. In forward reaction, these 2 will become the reactants and HI will be the product. And after concentration of the product ini adalah lebih tinggi berbanding these 2 reactants, maka reverse reaction will take place. So apabila reverse reaction takes place, HI will be the reactant and these 2 will become the products. So in reversible reaction, both direction of reaction boleh berlaku sehinggalah keseimbangan tercapai di antara forward and reverse reaction. Now, let's watch a video regarding dynamic equilibrium. Scan this QR code to watch the video. This is the concentration time graph for a reversible reaction. And now we are going to study the decompositions of N2O4 gases into NO2 gas. As in the forward reaction, N2O4 will become the reactant and NO2 will be the product. At the beginning of the reaction, di permulaan tindak balas, concentration of N2O4 will be decreases one time until time T1, and the concentration of the product will keep increases two times until time T1. So why concentration of the product will be increases two times? This is because we have this value 2 in the stoichiometry coefficient in the balancing equation. So as the reaction proceeds, rate of forward reaction will be decreases. Okay, kenapa rate forward reaction decreases? Ini adalah kerana concentration of the reactant will be decreases as the reaction proceeds and concentration of the product will be increases. So apabila concentration of the product is increases or higher than the reactant, rate of reverse reaction will be increases. So tidak balas berbalik akan berlaku. At T1, the rate of forward reaction is equals to the rate of reverse reaction. So after time T1, concentration of N2O4 and NO2 will remain unchanged or constant. Okay, ini bermaksud pembentukan ataupun formations of NO2 dan juga consumption of N2O4 in this chemical reaction akan berlaku dengan kadar yang constant. Okay, pembentukan masih akan berlaku dan penggunaan N2O4 juga masih akan berlaku. So hence reaction will not stop. So at this point T1, the system is said to be in dynamic chemical equilibrium. Characteristics of system in dynamic equilibrium. A system is said to be in dynamic equilibrium if it is in closed system, bekas yang tertutup ataupun sistem yang tertutup, and the reaction did not stop after achieving dynamic equilibrium. Rate of forward reaction equals to the rate of reverse reaction, and the concentrations of product and reactant, pressure and colors are constant after the system achieving dynamic equilibrium. So as you can see in these two images, this is the lines for T1, iaitu masa di mana system has achieving dynamic equilibrium. So as you can see in the first graph here, let's say from A forming B. A is the reactant and B is the product. So at the beginning of the reaction, rate of forward reaction will be decreases and the rate of reverse reaction will be increases. Ini adalah kerana pada permulaan tindak balas, apabila A bertukar menjadi B, concentration of A will be decreases and concentration of B product will be increases. So due to this reason, rate of forward reaction will be decreases. And as the concentration of B is higher than A, so reverse reaction will be more favored. Okay, tindak balas reverse akan menjadi lebih favorable. So in this case, B akan digunakan untuk forming A. So in this case, rate of reverse reaction will be increases as we have more concentration of the B. So this rate of forward and reverse reaction will keep changing, okay, will keep increasing and decreasing sehinggalah tiba pada masa T1, iaitu masa di mana system has achieved dynamic equilibrium. So as the system achieving dynamic equilibrium, rate of both forward reaction and reverse reaction will be equal. And in the second graph, we can see that concentration of the reactant will be decreases until time T1, and the concentration of the product will keep increases until time T1. So, apabila this reaction has achieved time T1 over here, which is masa di mana sistem telah pun mencapai dynamic equilibrium, so we can observe that there will be no change in the concentration of the reactant and product. Maksudnya, reactant dan juga produk tidak akan mengalami sebarang pengurangan dan penambahan anymore, but they will keep producing and keep using pada kadar yang constant. Okay, ini adalah kerana tidak balas tidak akan berhenti. So, production of the product and the consumption of the reactant masih akan berlaku tetapi dalam kadar yang sama, okay, dalam kadar yang constant. So, to understand what we have discussed just now, you boleh imagine kita ada satu bekas yang mengandungi air dan kita buka pili di atas dan juga pili di bawah. So, in this case, we can see that the level of the water in this container tidak akan berubah. Okay, walaupun kita buka pili di atas, okay, which means kita masukkan air ke dalam bekas, but at the same time kita akan buka juga pili di bawah. Okay, so ini menunjukkan bahawa in the sistem yang telah pun mencapai dynamic equilibrium, produk akan masih dihasilkan dan reactants akan masih diguna pakai, tetapi perubahan mereka adalah constant. Condensation dan juga evaporation adalah another example of reversible reaction, and the equilibrium between these two can only be attained in a closed system. The law of mass action or equilibrium law. So this law of mass action states that multiplication of products raised to power according to stoichiometric ratio divided by multiplications of reactants raised to power is known as a constant. Hasil darab produk yang mempunyai power according to stoichiometric ratio dibahagikan dengan hasil darab of reactant yang mempunyai power dikenali sebagai constant. So, symbol constant is K, iaitu equilibrium constant. So, K ini kita panggil sebagai equilibrium constant. And equilibrium constant K varies with temperature. So, this is one of the important concept yang you kena tahu. Okay, berbeza temperature, maka nilai equilibrium constant juga akan berbeza untuk same chemical reaction. This is the way to write equilibrium constant K for a specific chemical reaction. So suppose that we have this general reversible reaction di mana this capital A and B adalah reactants and capital C and D adalah products. Okay, meanwhile the small letter over here refers to the stoichiometric coefficient as in the balancing equation. So in order to write equilibrium constant expression K, so according to the law of mass action just now, K is a constant, so K equals to multiplication of the product, hasil darab of the product, okay, raised up to some powers according to their stoichiometric coefficient or ratio, divided with the multiplication of the reactants A and B raised up to certain powers according to the stoichiometric ratio as well. Okay, so by doing this, maka you dah dapatlah satu equilibrium constant expression for this chemical reaction. So Kc, what is Kc? Kc is the equilibrium constant, okay, but that is for the concentration term. Next, you are going to learn what is homogeneous and heterogeneous equilibrium, and then you will learn on how to write expressions for equilibrium constants K in terms of concentration and in terms of partial pressure for both homogeneous and heterogeneous system. And we will use this equation Kp equals to Kc RT power of delta N to solve equilibrium problems. And you are going to learn on how to calculate Kc, Kp, and the quantities of species present at equilibrium. There are two types of equilibrium. The first one is homogeneous equilibrium. Homogeneous equilibrium refers to all reactants and products are in the same phase. So for example, we have decompositions of these gases N2O4 to form gases NO2. So since reactant and products involving the same phases, maka this reaction is classified as homogeneous equilibrium. And for the heterogeneous equilibrium, reactants or products has two or more phases, okay, in the full chemical equation. So for example, in the reaction or decompositions of NH4Cl in solid form, okay, to form ammonia gases and HCl gases. So here we have two different phases in this chemical equation. So this chemical equation is classified as heterogeneous, as having heterogeneous equilibrium. For homogeneous equilibrium, perhaps we can write their Kc and Kp expressions. So in order to write Kc and Kp expressions, we need to have a balanced chemical equation dahulu. So as in this equation, we have nitrogen gas reacting with 3 mole of hydrogen gas to form 2 mole of ammonia gases. So these two adalah reactants and ammonia will be the product. So since all reactants and product are involving the same phases, iaitu gases form, maka this is the example of homogeneous equilibrium. So from this balanced chemical equation, we can write the equilibrium constant in terms of concentration. So ingat lagi tak macam mana nak tulis equilibrium constant? K equals to concentration of the product raised up to the power according to stoichiometric ratio bahagi dengan concentration of the reactants, okay, bahagi dengan multiplication concentration of the reactants raised up to some powers. So in order to write equilibrium constant in terms of concentration Kc, so Kc equals to the concentration of the product raised up to some powers according to the stoichiometric coefficient divided with concentration of the products raised up to the power according to the stoichiometry ratio. So this is the equilibrium constant expression in terms of concentration Kc. And for the Kc, we will use this square bracket, okay, showing that ini adalah equilibrium concentration. So these concentrations of the product dan juga reactant di sini adalah equilibrium concentration. And in order to write equilibrium constant in terms of pressure, iaitu Kp, so Kp equals to partial pressure of the product, which is ammonia, raised up to some power according to the stoichiometric ratio, bahagi dengan partial pressure of nitrogen gas times partial pressure of the hydrogen gas. So don't forget here we have 3, so that 3 will be raised up as power. So P adalah equilibrium partial pressure of gas, dan untuk menulis Kp expression kita akan gunakan bracket bulat like this. But for the Kc expression, we will use this kind of bracket, iaitu square bracket, to show that ini adalah equilibrium concentration. Okay, and the symbol of P here merujuk kepada equilibrium partial pressure of the gas. So, apabila kita mempunyai fasa gas, okay, fasa homogeneous gas, maka we can write both Kc and Kp. Tetapi sekiranya kita mempunyai homogeneous equilibrium yang mana fasanya adalah aqueous, kita hanya boleh menulis Kc expression sahaja, and there will be no Kp for aqueous solution. As in this example, we have reactants and all products dalam fasa yang sama, iaitu aqueous. So ini adalah another example of homogeneous equilibrium. So in order to write the Kc expression, maka kita akan tulis the multiplication of the products divided with the reactants di sini. So since it is aqueous condition ataupun aqueous solution, maka we are able to write the equilibrium constant in terms of concentration. But for Kp, okay, we cannot write the Kp expression for the aqueous solution because aqueous has no partial pressure. This equation is the example of heterogeneous equilibrium kerana okay, kita ada perbezaan fasa di dalam reaktan dan juga produk. So in heterogeneous equilibrium, please bear in mind that concentration of pure liquids and solids are constant and they are excluded in Kc or Kp expression. Okay, sekiranya awak nampak ada fasa liquid ataupun solid di dalam chemical equation reversible kita, maka kita tidak akan masukkan the symbol of the reactant or product, okay, yang berada dalam fasa liquid ataupun solid ke dalam Kc maupun dalam Kp expression. So, in order to write the equilibrium constant in terms of concentration Kc, maka kita hanya akan consider fasa gas dan aqueous sahaja jika ada. So, here kita akan menulis okay, this HCl dan juga ammonia because they are in gaseous form. So Kc equals to the concentration of the ammonia raised up to some power, okay, darab dengan concentration of the HCl, okay, and we supposed to divide dengan concentration of the reactant, but since reactant is in solid form, maka the value adalah 1. So this will be the Kc expression in terms of concentration. And for the equilibrium constant in terms of partial pressure Kp, so Kp equals to partial pressure of the products. So this will be the multiplication of the product divided by divided by the partial pressure of the reactant. So since reactant is in solid form, okay, maka dia adalah constant and the value adalah 1. So this will be the Kp expression in terms of partial pressure. In this example, since we have aqueous and gaseous form in the reactant and products, maka we are able to write equilibrium constant in terms of concentration. So Kc equals to concentration of the product divided by concentration of the reactant. But since H2O is in liquid form over here, so H2O will be excluded, okay, from the Kc and Kp expression. So for the Kp is only effective for gaseous form sahaja. We can write Kp apabila kita ada gaseous form. So in this case, the expression of Kp will become Kp equals to 1 over partial pressure of SO3. Okay, kenapa 1? Kerana Kp hanya boleh ditulis untuk gaseous form sahaja. Untuk aqueous form, kita tak boleh tulis Kp expression.
So the value on top adalah 1.
Okay, bahagi dengan partial pressure of gaseous form in the reactant. And since kita ada 1 sahaja gaseous reactant, So that is the reason why we have partial pressure SO3, okay, at the bottom there. And please remember, okay, for this is the most important fact, the concentration of the pure liquids and pure solids are constant, and they will be excluded in Kc or Kp expression, okay, because they are constant. Dependence of the value of equilibrium constant. Suppose that we have this reversible reaction with the Kc value 400 at 200 degrees Celsius. So this is our original Kc equation and Kc value. By multiplying or dividing this original equation with certain factors or numbers, that will change the value of the Kc. So as in this example, it seems like kita bahagikan this original equation dengan 2 to get this new equation. So by doing this, kita akan lakukan operasi Kc power of 1/2, and hence by doing this, awak akan dapatlah jawapan the new Kc as 20. And then by doing reversing the original equation here juga akan menyebabkan value of the Kc will changes. So for the case of reversing equation, so to find the new Kc, kita akan simply lakukan operasi 1/Kc. So by doing 1/Kc, okay, you will get the value of the new Kc for this reverse equation here. And if you are doing reversing and multiply this equation with certain factors, definitely the value of the Kc also will changes. So to know on how we can get this value, kita akan discuss more in the tutorial. Relationship between Kc and Kp. If the delta n not equals to 0, value of Kc is not equals to Kp. So in this case, in order to find the value of Kp from Kc and vice versa, we will use this formula. Kp equals to Kc times RT power of delta n. So what is the delta n? Delta n is number of mole of gaseous products minus number of moles of gaseous reactants. So remember, if the number of delta n, or if the value of delta n is not equals to 0, the value of Kc is not equals to Kp. So by knowing the value of Kc, we can calculate the value of Kp and vice versa by using this equation. But if the delta n equals to 0, the value of Kp will equals to the value of Kc. Ini adalah kerana daripada formula Kp equals to Kc RT power of delta n apabila delta n adalah 0. So let's substitute the value here. So apabila RT kuasa kosong, so the Kp akan equals to Kc kerana RT kuasa kosong bersamaan dengan 1. In example 1, the equilibrium concentrations for the reaction between carbon monoxide and molecular chlorine to form COCl2 gas at 74 degrees Celsius are given respectively. Calculate the value of equilibrium constants Kc and Kp. So in this question, we know that carbon monoxide CO and molecular chlorine Cl2 are the reactants, and COCl2 is the product. And also kita ada equilibrium concentrations for all substances. Okay, so di sini adalah equilibrium concentrations untuk setiap satu CO, Cl2 dan juga COCl2. So by having these informations, you are going to calculate the equilibrium constant Kc and Kp. So in this example, we are going to solve the value of Kc and Kp from the given equilibrium concentration or equilibrium partial pressure. So from the question, firstly, of course, you need to start with writing the balancing chemical equation. And then we are about to find the value of Kc. And since we already have the equilibrium concentrations over here in the soalan, maka from the balanced chemical equation, first you have to write the Kc expression. So Kc equals to concentration of the product over concentration of the reactants. And then kita akan substitute the equilibrium concentrations for all substances. And we will get Kc value as 216. Next, to find the value of the Kp, firstly you have to check the value of the delta N dahulu. So delta N equals to number of mole of product minus mole of reactants. So for the product we have 1 mole minus dengan reactants mole is 1 tambah 1 which is 2. So 1 minus 2 equals to -1. And since the value of delta N is not equals to 0, so the value of Kc is not equals to Kp. But by knowing the value of Kc, we can identify the value of the Kp. Okay, bagaimanakah cara dia? Kita akan gunakan formula Kp equals to Kc times RT, power of delta N. So what is R? R adalah gas constant 0.0821 ataupun 206, and temperature adalah 74 degrees Celsius, and please convert this one in Kelvin. Okay, so by having this, maka kita bolehlah cari value of Kp. So Kc is 216 darab dengan R times temperature, okay, power of delta 1. So by doing this mathematical operation, so you akan dapat Kp is 7.58. In example 2, you are going to calculate the equilibrium concentrations or equilibrium partial pressure from the value of Kc and Kp. So dalam example ini, you akan menggunakan value of Kc dan juga Kp in order to find any of these equilibrium concentrations ataupun partial pressure. Nitric oxide, oxygen and nitrogen react by the following chemical equation. In the atmosphere, equilibrium partial pressure of oxygen and nitrogen gas are given respectively. And also we have the value of the Kc in the equation at 298 Kelvin. And what is the partial pressure of NO in the air we breathe? So in this soalan, you are going to find the partial pressure of NO. Dan kita juga dah ada nilai equilibrium partial pressure for oxygen and nitrogen gas. So by having this information, supposedly kita boleh tulis Kp expression untuk that chemical equation. So Kp equals to partial pressure of nitrogen gas times partial pressure of oxygen gas divided with partial pressure of NO. So please make sure this equation are balanced correctly. So since we have 2NO in front of this equation, so PNO will raise up to power of 2. So di sini, we already have the partial pressure of oxygen, partial pressure of nitrogen, but we don't have the Kp value in order to find the partial pressure of nitrogen oxide. But we do have the value of Kc in the question. So in this case, by having the value of Kc, you will be able to find the value of Kp. So by having the value of Kc in the equation, you will be able to find the value of the Kp. But before we find the value of the Kp, you have to check for the value of delta N dahulu. So delta N equals to 1 plus 1 for the product minus 2 mole for the reactant. So the answer for delta N adalah 0. So in this case, apabila delta N adalah 0, maka the value of Kc equals to the value of the Kp. So here, Kp equals to 2.3 times 10 power of 30. Okay, so why we can get this value? Ini adalah kerana Kp equals to Kc 2.3 times 10 power of 30 times RT power of 0. So this will give the value of Kp equals to the value of the Kc. So after finding the value of the Kp, so next we are going to insert the value of the Kp into the Kp expression.